Good afternoon, and my name is Joe Bishop from Sandia National Laboratories, and I'm happy to open up the semi-plenary sessions of the Congress. It's my honor to introduce Anima Anandkumar. She's a Bren Professor of Computing and Mathematical Sciences out at Caltech. Interestingly, or amazingly, she's also currently the Senior Director of AI Research at NVIDIA, and she'll talk about how she combines both of those, and it's very exciting. She received a Bachelor of Technology from IIT Madras. She has a PhD in Electrical and Computer Engineering from Cornell. Before starting in her current role, she was a postdoc. She did postdoc research at MIT. She was Associate Professor at UC Irvine. She's received several honors, including the IEEE Fellow, an ASME Fellow, Alfred P. Sloan Fellowship, an NSF Career Award, also an AFOSR Young Investigator Award. Also, she has had faculty fellowships from Microsoft, Google, Facebook, and Adobe. And she's also a member of the World Economic Forum's Expert Network. So with that, Anima.
Thank you, Joe, and thank you, Rekha and Jim as well for inviting me. It's my first time in this community, but I've been learning a lot from people in your domain. I work closely with Kaushik Bhattacharya at Caltech and Andrew Stewart. They were really instrumental in helping us develop this neural operator framework that I think is the principled approach to asking for surrogates for numerical solvers, right? And one that we can guarantee can faithfully capture the complexities of many real-world phenomena, including those in mechanics. And so what differentiates this from other standard AI approaches? There's convolutional neural networks, transformers, right? So all these networks are already there, and there are a lot of people applying it to problems in PDEs. So why neural operators? And why is, in my view, why we should be only doing neural operators and not those other approaches if you want to get to the ability of capturing the underlying solution operator, not just solving one instance of a PDE's problem or to just take a solver and add some correction terms, but really to be a true surrogate that can, in some cases, be a replacement for numerical solvers. So how do we first of all develop the theory for that, and what are some results we already have, and how all of you can approach that. We have now open source libraries and easy to use examples. So hopefully it's something that all of you can participate in as well. Yeah, so multi-scale processes just are, almost every scientific problem has challenging complex phenomena that we need to capture, right? So if you think about molecular dynamics, there are multiple scales, sometimes all the way from quantum level effects to higher force field and other models. And of course, if you're looking at the weather of this planet, that involves phenomena at so many different scales, from cloud turbulence to microphysics and precipitation models to, of course, larger convection and storm phenomena. Yeah, so how do we capture all of this in one model, right? And that's where I also want to point out that this kind of phenomena are not typically what you think when you look at standard neural networks. If you think about a computer vision model, it only expects data at one resolution, and you can apply it to test data at the same resolution, right? But that's not how these phenomena are. They have multiple scales of information. Sometimes you may be able to capture some of that with data, right? But if the data is too low resolution, it doesn't have all the information about the finer scales. So you could add equations. In many cases, we know the physics, we know the equations, even if we don't know all the parameters that are part of this equation. So we have a lot more information than what we typically have when we train machine learning models. In the typical case, we just have data, right? If you look at text and image models, there's just data and nothing else. But in scientific problems, we have equations such as partial differential equations, we have symmetries, we have all kinds of other constraints. So that's the other aspect. How do we design a physics-informed approach that can help us capture all the scales, even if the data is not available, that can inform us of all these scales that are present in these natural phenomena. And indeed, the climate modeling is one, right, kind of a poster child for this challenge, because if you really want to faithfully model this, you should be computing, or rather solving these equations, right, Navier-Stokes equations, at a very fine scale. So, you need to go down to 100 meters or meter scale resolution in order to capture the cloud turbulence. But this is so much out of the reach of current, even bigger supercomputers. So brute force solutions with numerical solvers today are just not able to go to the finer scales of solutions we want in many cases. So given that, what is then the solution, right? So I feel like AI can help us accelerate this process of solving PDEs in many domains. And that's a combination of advantages that AI presents. For instance, one, and I would say the most important one, is these machine learning models are driven by data. They're driven by also, right, providing equations as loss functions. And they can try to find their own path to the solution. So in the process, you hope that they learn better nonlinear features. So maybe they come up with a new way of solving these equations, right, through different nonlinear transformations compared to numerical solvers. Numerical solvers many times require a very fine grid in order to guarantee convergence, and it's iterative and slow. But with machine learning methods, there is the potential. I don't know why the mic just keeps doing that. I don't know if you hear that, but there's always anyway, I hope that, so with the machine learning method, I think there is the potential now to learn new paths to solution that could be much faster. And in fact, that's what we show in our experiments, that when you learn features through neural operators, we can show the ability to solve these equations by taking much larger steps, right? You don't have to limit to a fine grid effectively. And still, and this way we can get a big speed up. And the other benefit, of course, is the benefits of hardware acceleration and hardware efficiency. Many of these tools that we use in our machine learning models have abilities like mixed precision, of course, good GPU utilization, right? All these that has seen a lot of interesting development because of the advent of large language models, right? There is always this need to keep bringing the cost down, the costs of compute, the costs of networking, how much can you compress these models? So we can harness all that once we make our PDE solvers also to be machine learning based. And this, yes, in principle, you could take the numerical solvers from CPU and move them to GPU, but there's so many domain-specific solvers, right? And it's been a cumbersome process to move all of that to GPU directly. And that's still useful if you can do that because you can generate training data at a faster pace. But with machine learning-based models, it's much more direct. The moment you have a good surrogate, you can run them on GPUs, and you can try principles like mixed precision. I won't get into the details of it, but we know with traditional numerical methods, you need very high precision, right? In fact, double precision in many of the cases. But here we show even half precision FFT calculations can work well in many of the neural operator models that we provide for solving fluid dynamics and other PDEs. And so I think there's a lot of potential for speed up and acceleration by looking towards using machine learning-based methods for solving PDEs and other scientific modeling that requires capturing multi-scale processes. Yeah, so to give you an overview of how our results look like, this is kind of a starting case for our neural operators. In particular, this is a Fourier neural operator. In a minute, I'll tell you what that specific model is and what are the principles. But what I want you to take away, the main point of this talk, is this ability to train on lower resolution data and be able to directly predict at higher resolution, right? So with a standard neural network, you wouldn't be able to do that because standard neural network expects inputs and outputs at fixed dimensions that are fixed during training. Of course, on top of a standard neural network like UNet, we can add interpolation, like trilinear interpolation, I think is what we did here. So you can always do that. But that standard interpolation turns out to be very poor when you try to extrapolate beyond the resolution of the training data. So here you see the wave numbers corresponding to the training data, and this portion here is the wave numbers that we want to test. That is extrapolation. That was never seen during training. And so what you see with Fourier neural operator in blue here is it pretty much follows a similar trend as the ground truth, right? So in this example here, there is a drop-off of energy with respect to the wave number, and it follows a similar trend. On the other hand, if you take a standard neural network and do interpolation on top, there is severe distortions at finer scales. And we know, I mean, I'm sure you're better experts in saying this, that if you have these kind of distortions at finer scales, that's not a faithful surrogate, right? You cannot trust the system in many scenarios that does require such fine-scale information to be incorporated. And I think that's the principal information that I want to convey in this talk, that you can always take a standard neural network and try to do some standard interpolation, fixed interpolation on top of it to be able to predict finer scales, but most of the time it's very wrong, right? So there's severe distortion, so you don't want to do that. And on the other hand, neural operators have the ability to capture different scales. And first of all, it's natively able to predict at any discretization of data. So you can take any query point in a continuous domain, the domain of your problem, and ask for predictions once the model is trained. And I think that's an important difference, that principally it's like neural operators are a superset of neural networks. That's how you want to think of them. And so currently what we saw was these Fourier neural operators here in blue are able to follow the trend of the ground truth, but they were not perfect, right? And there's an information gap. I mean, there's no way it could perfectly match the ground truth spectrum because it wasn't shown that information during training, right? So you only had limited resolution training data. So you cannot expect the model to magically perfectly match the ground truth spectrum beyond the resolution of the training data. But we can fix this. We can make it completely faithful and have the ability to perfectly match the ground truth spectrum by being able to look at a physics-informed approach. So in addition to the training data that's only available at lower resolution, we can now add constraints, the constraint that you want to make the equation, right? So it's what we call an equation loss function. You want to check if the equation is true or not and penalize based on that. So when you add the PDE loss function, you can see here in green it's on top of the ground truth. So this way we can capture all the scales of information perfectly in this example, right? And so that's what the neural operators have the capacity. They can take training data at multiple resolutions if available. And they can extrapolate and predict at higher resolutions than what was available during training. If in addition, you also know the equations, such as these partial differential equations, you can add that as loss functions during training, right? And you can further use that information to really be able to capture all the scales of the phenomena and get a faithful reconstruction of the underlying operator. So the underlying operator here is the solution operator of Navier-Stokes, right, for this setting. Yeah, so that's really the point I wanted to convey here, that neural networks are built to work only at one fixed resolution. So they expect inputs and outputs at fixed dimensions, and if you want to move away and go to a different resolution, you can add interpolation on top, but most of the time it doesn't work well. And on the other hand, we know numerical solvers, right, can work on different grids, even different shapes of grids. And we want frameworks, machine learning frameworks, that can faithfully recover these kind of operations and more generally be able to capture solution operators on all kinds of different manifolds. And so that's the aspect of how neural operators are different from neural networks, because technically what they're doing is learning mappings from one function space to another function space. So this function space, in the case of PDEs, the input can be the initial condition function, right? And the function can be some continuous domain, defined on a continuous domain, initial and boundary conditions, and the output is also a solution function defined on the continuous domain. Of course, in order to try and learn this operator from data, you're only given discrete data, right? It's, of course, if you're given the full function, it's very easy to learn the operator. But usually you only have a finite discretization or finite resolution of data available. So the next question becomes, how do you use that and still come up with an approximation of the underlying operator, meaning you're capturing the continuum even though you're only given discrete data during training. And so this is what we, the details are in the papers. We're able to guarantee that neural operators are able to, you can allow querying anywhere in the domain, so it's not just limited to the grid of the training data. And not just that, there's a nice kind of a uniform convergence result irrespective of the kind of mesh refinement. As long as you do proper mesh refinement, there's a notion of nestedness and some nice properties, right? You can take any kind of mesh refinement that satisfies those properties, and we guarantee that neural operators converge to the same unique limit, which is an operator. So this means you're able to do predictions anywhere in the domain, and there's also a notion of consistency that if you keep refining your grid, there is a convergence of this solution. And it doesn't matter how you're refining the grid, you can do it in multiple ways, and it converges to the same operator. And so that's a nice property that, in a way, you don't have to worry about how, right, you're going to discretize to try and arrive at a solution. In the limit, they're all the same. And that's the thing that only neural operators have. So, what we call here neural operators are the ones that have this property of convergence. And if you just did neural networks and did interpolation on top, you will not get universal approximations. So they cannot capture every possible operator that is mapping between two function spaces. Whereas neural operators, we guarantee, is a class of universal approximators. So meaning you can capture any continuous operator that could also be a nonlinear operator. So meaning they have the capability to do this, right? So that's important. And if you take only neural networks, they don't have the capability to approximate operator as well. And same with neural networks with interpolation added on top. So they just don't have the capacity. Yeah, so now the question is, I advertised all the nice properties of neural operators, but what are they, right? So I showed you some results. I told you this is the thing, but what is it? So yeah, let's go step by step. And really a lot of this, right, builds on function analysis and how we think about solution operators of PDEs. And always the starting point to me is a simple case. And in this setting, that would be linear partial differential equations. So we know if it is a linear partial differential equation, the solution to that is an integral linear operator, right? So you're taking the Green's function or a kernel and convolving with it. And so we know if we could design an architecture that would have approximations to this kernel integration, we know that that would also be able to get an approximation to solution operators for all linear partial differential equations. Of course, that's not everything because we have a lot of nonlinear PDEs, right? We haven't yet gotten to that. But just as a starting point, we know for linear systems and linear differential equations, we know the structure of its solution. And so given that we know the structure, you can think about now asking, how do I learn this kernel and how do I integrate over it? In some cases, like the heat diffusion equation, you may even have analytical solutions in some special cases, right? But in general, we don't have analytical closed form solutions for Green's function. You would have to numerically estimate it. So you could think of approaches where we try to learn the kernel from data, and we try to discretize this integration, and that is a possible architecture for a neural operator, for linear systems. So we have several such approaches. I'll come to that in a minute. But what we want to do is not just limit to linear systems, right? So we want to solve general nonlinear systems and be able to learn solution operators from data or equation constraints. And so given that, a simple trick, right, this is very intuitive, you don't just limit to the block that computes the linear integral operators. On top of it, you add some nonlinear activations. And by composing this, now it becomes a universal approximator that can capture nonlinear operators, right, that can approximate nonlinear operators. And this principle is very much on the same lines as what you do in a neural network. In a neural network, instead of a linear operator, usually you have a linear function. If it's a fully connected neural network, it's matrix multiplication, right? So that's a linear function. On top of it, you add activations such as ReLU, and then it becomes an expressive model that can, in principle, approximate any finite dimensional function. This is the counterpart of that. With neural operators, you can now learn integral linear operators that are composed with nonlinearity. And by learning this together, you can now come up with faithful approximations for any nonlinear operator. And so this, now is a general framework of models, right? I haven't yet told you what are the choices of architectures I want to make in order to come up with approximations for this block that computes integral linear operators. What are the choices of nonlinearities? How many layers? So all of this is on similar lines as you would approach a neural network. Those are specific architecture choices you make. But at this point, what this result says is this is a general class, right, that has the capability to come up with universal approximations for any nonlinear operator. And so one architecture we've been using a lot that has been effective is what we call Fourier neural operator. And the principle for that is very simple, right? If we specialize the integral linear operator to be convolution operator, you can compute that very efficiently in the frequency domain. And so you can do the learning in the frequency domain where you're learning coefficients for different frequencies. And coming back to the standard domain, then doing nonlinear activations. For instance, we use GELU because ReLU sometimes, ReLU doesn't have second derivatives, and we need that for many of our equations. But you can do all kinds of choices for nonlinear activations. This is some math. I wouldn't worry too much other than just reminding you that, right, like you can do convolution as multiplication in the Fourier domain. And so by doing this change of basis, I can learn much more efficiently in the Fourier domain what are the weights on different frequencies. And so that's how I can come up with an efficient framework that also exploits the bias in many domains, that the signal is better expressed in the frequency domain, right? There are solvers that are based on spectral domain, but the difference I want you to remember is that it's not just a spectral solver, because we have nonlinear activations in between multiple such blocks. And what that enables us is to learn different features, right, that are different from just a spectral basis. And so we can combine this power of nonlinearity along with inductive bias of the frequency domain, as well as the ability to do predictions at any resolution, because we can do Fourier transform at any resolution, right? Or even non-uniform grids, but I'll come to that in a minute. But I hope the principle here is clear that we can come up with now approximations to convolution operator by learning coefficients over different frequencies. But we do not just stop there. We do nonlinear transformations and we learn again. And so this way you can capture a much bigger part of the spectrum than if you only took one operation here, and especially because we are thresholding the higher modes here. So we only keep the low frequency modes when we come back to the standard domain, which acts as a nice regularization and gives better generalization, especially at higher frequencies. So we can afford to do this kind of filtering because we have nonlinear transformations. So in a way, it's combining the best of frequency domain analysis and filtering along with nonlinear transformations and data-driven approach to learn new and better features from data. Yeah, and so that's what enabled us to now come up with extrapolation to higher frequencies beyond what was seen during training, and still follow the overall trend that we see that is similar to the ground truth. I'll just comment very briefly also how to take this to non-irregular domains, not just the regular grid. Regular grid, you can do fast Fourier transform, and that's very efficient. And what we instead do with irregular grids is we transform it into a latent space where we still do fast Fourier transform. So that is very efficient. We want to not sacrifice the computational efficiency of doing fast Fourier transform on a regular grid. So we'll keep that property, but learn a transformation from the physical space to the latent space, where we can handle also irregular grids. And this one, is predicting, it's a plastic forging problem and asking if it's impacted by a frictionless rigid die on top, what is the deformation? And we can do this for all kinds of different initial conditions, right? So this is just one example, but we can do for all different conditions once the model is trained. So it's not just learning one specific shape, it's able to predict different shapes depending on the initial condition. And it's also much faster than what we see with our numerical methods. And as I mentioned before, another important aspect that we want to exploit that's available in these domains is equations, right? So you have equations, and so far, what we assumed with the use of neural operators is that training data is available. Maybe you ran the solver before, you collected the data where there are different initial conditions and their solutions, or you observe the data. For instance, in weather forecasting, it could be also just the observational data, right? But so far, it's only data and none of the knowledge about the physics. And we can change that. And one simple way to change it for PDEs is just to enforce the equation laws. You take the equation, you check whether the equation holds or not, and if not, you take a gradient and encourage it to satisfy the equation. And so we can combine the two. These are some specific details showing how in the Fourier domain you can get exact gradients, and you can also do methods like Fourier continuation and get really precise gradients, right? So that's a detail I will not get into, but there's also a lot of nice designs we can do to make this whole process even more effective. Yeah, and as part of that, we can further keep improving the errors, or rather the accuracy of what we've learned. So far what I talked about was operator learning. I have a bunch of initial conditions, and then I have either the data that corresponds to the solution of those equations, or maybe also the equation loss function. I can combine that here. But I can further improve the solution of a specific instance of the PDE by taking the loss over that PDE, right? So I can check what my pre-trained model is able to predict, and I can further improve it by enforcing the equation loss. And with that, we can further improve, and that's how we can get very high fidelity solutions. And as you saw here when I talked before, this way we can perfectly match the ground truth spectrum, whereas in a data-driven method, that would be impossible because there's a fundamental information gap when you're given only coarse resolution data that you wouldn't be able to perfectly get to the super resolution setting without further information. And adding the physics information helps close this gap. You can also incorporate this for other settings such as transfer learning, right? So you can train here in this example on one Reynolds number and transfer it to another, right? So if you did that in a purely data-driven manner, that's a big distributional shift. On the other hand, in the physics-informed setting, you know precisely what changed in these equations. So the model can much more quickly adapt to the change in settings because it's aware of these equations. And so I think that is also much more effective because of the guardrails of physics around a data-driven model. Yeah, so let me show you quickly some of the applications where we've been scaling up these methods. One is weather forecasting, where we are able to show much faster ability to forecast at almost similar medium range capabilities as the current numerical weather systems. And in this visualization, you can see how atmospheric rivers are being predicted. And there's some more details. There's also an open source version of the model, and we are continuing to update it to the latest one. But really the thing I want to emphasize is speed is great, but what is, will speed help us with accuracy, right? And in the case of weather forecasting, it's true, because what you can do is you can create much larger ensembles for tail risk assessment, such as extreme weather like hurricanes. You'll be surprised, at least I was surprised when I learned that the current weather systems keep only about, or rather compute only about 51 ensemble members. And with so few ensembles, you miss the tail of the distribution. Whereas in our system, because it's tens of thousands of times faster, you can parallelize and compute thousands of ensemble members. So you get much more accurate statistical scores compared to what we are able to do today. And in this visualization, you can see that our model is able to kind of capture the physics of what a hurricane looks like and with more ensemble members really get to good tail risk assessment. So this is just making the point that if you only took 50 ensemble members where you put up the initial conditions and looked at what will happen to the wind speeds, you miss the tail, right? You miss the extreme weather events of high wind speeds. And that is bad, because that's when it's hurricane storms and all these that you don't want to miss. And so this is where I argue, even if you have similar overall medium range capabilities, our speed up leads to much better assessment of tail risks, which is very important for extreme weather. And so I also want to emphasize that there are many models that have been proposed for data-driven weather forecasting. So what's unique our model is we can run our model for very long, in fact, almost a year long, even though we trained it only to predict for the next 6 hours, right? And we could roll out after that. And our model kept being stable, whereas the model here on the left blows up very quickly. And the reason is we incorporated the spherical geometry. We do spherical harmonics, so it's effectively a Fourier transform on a sphere. And so having that inductive bias and knowing the geometry of the domain helps us extrapolate much, much beyond, right? We are rolling out much further in time than what the model had seen during training, and it's able to keep the faithfulness. And I think this is where the notion of how much domain knowledge and constraints to put into these models becomes important. So there are many other applications as well we've been doing, such as multi-phase flow systems for storing carbon dioxide underground and asking, can we model the pressure buildup and the evolution of the gas plume? Here you can see it's highly nonlinear, and we are able to give high-resolution predictions, and it's about 700,000 times faster. So we can do very fine grid predictions or fine resolution predictions of these highly nonlinear phenomena. So we're also able to directly learn from observational data and do that in real time for fluid flow. And this could be very effective when it comes to handling turbulence, right? In airfoil wings. Here in another project, we're looking at how with reinforcement learning, you can learn turbulence effectively. And at Caltech, we have collaborations with Mori Garib and others who, where we can use these facilities to test drones. So it's really going all the way from learning to testing, right, in the real world settings, right? First in the lab, which helps us challenge these drones with high wind conditions and all kinds of different shapes of winds. Yeah, so there are many other settings as well where we continue to apply neural operators, and certainly others in the community are also exploring this from multi-scale, right, plastic deformation, nuclear fusion, and being able to predict disruption earlier, right, in real time, so before the disruption occurs, ultrasound imaging, and sometimes it's hundreds of thousands of times faster than what you can currently do with standard numerical methods. And so it's not just stopping at simulation, but really asking, once we have surrogates for these numerical solvers, what else can we do? So the other benefit is that these neural operator models are differentiable. So you can directly take derivatives when you're doing inverse problems. And so for instance, here we designed a better medical catheter by introducing these triangular shapes. And we optimized that using the neural operator method. So we can directly optimize in the design space, right? In this example, what should be the optimal shape of triangles to prevent the bacteria swimming upstream into the human body? And so this involved learning a model of the fluid flow and the bacterial density in it. And once we learned the forward model, we did inverse design optimization where we differentiated through the neural operator and directly came up with the optimal triangular shapes. And our collaborators, Kiera, the Reyes group at Caltech, 3D printed it, tested it, found that it reduced bacterial contamination by about 2 orders of magnitude. So this is where I think it can really be an exciting approach where you can do very accurate, not just simulations, but also design proposals first with AI and then go and physically validate that. We're also doing that in other settings such as mask design and lithography. That's very important for chip manufacturing. And so some of our collaborators at Lawrence Berkeley Lab have been exploring you thinking of neural operators as a foundation model that can capture multiple different systems of partial differential equations. Like what I had showed you before was Navier-Stokes, right? It learns on Navier-Stokes data, it predicts on them. But in this paper, what our collaborators showed was also somewhat different looking equations. You can capture all that in one model. And of course, it's an open question that these are fairly simple models and how this would hold up if the equations looked very different. And what is the value of training one model versus multiple separate models? But I think to me, that's an intriguing question. Yeah, so in the remaining maybe 1 or 2 minutes, I wanted to just also more broadly tell you other exciting directions in AI for science, right? So we've been using language models on genomes in order to be able to predict new variants of concern for coronavirus and be able to be prepared with new vaccines and drugs before the variants emerge. So in this example, it successfully predicted variants that were not seen during training time. We're also developing generative models for scientific computing where we are extending neural operators not just to learn deterministic mappings, but also probability distributions, right, that map from one function space to another. There's a lot of nice theoretical framework here we developed where we guarantee that ability to do that correctly. And we build on the notion of diffusion models, but now on function spaces. Just as a quick example here, you can see that even though we train on lower resolution data, we can generate now examples at higher resolution, and we can sample from the ensemble of initial conditions. We've also been looking into capturing the physics and symmetries in many domains, and in this example, what we did was to predict how well does the coronavirus spike protein bind with calcium ions using DFT surrogates. So doing a quantum chemistry prediction, and instead of DFT, use numerical methods, use an AI-based method to do that much faster. And so there are details about that. It's called OrbNet, but I won't get into that. There's also a lot of interesting questions of how we can go to solving robotics and embodiment, right? So I will not get into that. And thinking about agents that continuously interact with environments such as Minecraft here, and still talk to foundation models like GPT and combine the knowledge of GPT with exploration in these worlds. So anyway, I'll stop here, and thank you for this opportunity.
Thank you so much, Anima. That was a fascinating talk, very interesting work, and we have probably time for 1 or 2 quick questions. If anybody wants to come forward, and yeah, you get the mic there.
All right, thank you. Very exciting stuff. So I have 2 questions. One is how sensitive are the results you get out of these machine learning models to the architectures of the networks themselves? Do you guys have kind of one magic architecture that you can apply across the board, or do you have to custom tailor them to each problem? And the other question is the training cost. How long does it take? What computational resources do you need? Thank you.
Yeah. No, those are great questions. So we have a lot of best practices that we put in our library and examples, so I think that's a good starting point. And of course, the answer is it depends on the domain, right? I think maybe one difficulty for newcomers is the way you tune neural networks, and this is slightly different because you also want to keep track of what happens as extrapolation, see if it also captures finer scales well. And many people forget to kind of think of other ways to validate their models, and I would say that's still something people are getting used to. And the second one on training cost, it's much lower than many things you see in many examples. We barely have thousands of initial conditions that I showcased. So it's, it still needs some data, but not to the amount that you see, for instance, with language models. And the other aspect is as we add more of the physics constraints in the Pinot setting, we can reduce the data even further.
Pavel Bochev in the back, and that'd be our final question.
Thank you. Very nice, interesting, illuminating talk. It's actually a related question. So when you were showing your neural operator structure, it strikes me that it does resemble a lot the canonical Wiener architecture. So would it be fair to say that your neural operators are instances of Wiener architectures, which actually are also universal approximators?
Yeah, so I have to think which, the neural operator is a very general class, right? So I would say the Wiener architectures or others, or even the structure of the different numerical solvers are specific instances within this, right? So you can think of that as one instance, if that makes sense. But happy to chat more.
With that, thank you so much. Thank you.